Okay, so this video and the next video are going to be on differential equations. This video will cover the basics and modeling of differential equations as well as a general idea. The next video will be about solving differential equations and how we can do so in MATLAB. So this is the basics and modeling portion. So the basic form of a differential equation is that we have a derivative term and it's equal to some function of the term and time. Obviously, this goes very far. You know, f could be any function. It could depend on x. It could depend on time. It could depend on both. There's a wide variety of differential equations that can be made with just this simple condition. To have a better understanding of differential equations, I would highly recommend the 3 blue 1 brown video. It does a great job building an intuition, and I cannot stress enough that how useful that is in getting that intuition. From here, we're going to just model a simple second order system, the spring mass damper, which is by far the most common system in engineering that I'm aware of. And then we will explain why the difference between an exact and a numerical solution, and a little bit of reduction of order. So let me move this off to the side. So the first thing we're going to do is model a second order system. Now, the common system that we use is a spring mass damper. We have some mass, we have it attached to a spring with some constant K, and we have a dampener, which is a viscous damper with some constant B. And we will define our axes from here. This is the positive x direction. And so from here we just have to use Newton's second law to derive our expression. Newton's second law is force is equal to mass times acceleration. Both of these are vectors, but for our case we only have to worry about the x component. So what are the forces that act on this system? Well, if we were to displace our mass a small amount, what forces would act on our mass? Well, we would have the spring force, which acts against us. So let's say this is our mass. We have our force of the spring, Fk, and this would be equal to k times the displacement, right? Say we have some small displacement x. This is the force that would act on it, is k times x. We also have our viscous damper. The viscous damper also has a force opposing our motion, viscous damper. And for those of you who have taken a class on differential equations or dynamic systems and controls, you will know that this is proportional to the velocity, or the first derivative of the displacement. So we can see that both forces act against the motion. So if we combine this with Newton's second law, we get sum of the forces in the x direction equals mass times acceleration, while acceleration is the second derivative of x. The sum of the forces, well, we have negative Fk negative Fb is equal to mx double dot. Substituting in these two expressions, we have negative kx minus bx dot equals mx squared. And you know, there's a little thing that we neglected here, but we'll account for right now, which is maybe there is some other force, some external force that depends on time, or even that depends on time. And this will act in the positive direction. We will define that this force acts positive when it works in the x direction. So we can just add that here, f of t. And now we can solve this so that all the x terms are on one side. Pretty straightforward. Mx double dot. I'm moving these two here and then flipping it around. Plus kx equals f of t. And this right here is the second order differential equation of a spring mass damper. As you can see, it's very straightforward, and actually solving it is something you would learn in a differential equations class. Unfortunately, I can't get into it myself, but the idea is the same, which the idea would be computationally solving it would be taught in such a class. However, this equation makes sense to us in that we have some mass with inertia, and we have two restoring forces plus an external force. This could be zero, this could be non-zero. We will worry about that later. But these are the equations of motion for this specific system. Now, in a typical differential equations class, as I mentioned, we would solve this. We would assume the solution has some form e r to the t. We would solve for x dot equals r e to the rt. X double dot is equal to r squared e to the rt. Again, I'm not particularly qualified to teach this, but you would substitute these in, pull out a characteristic polynomial, and you would get a solution that looks something, depending on the cases, you'll have something that looks like this. C1 R1t plus C2 e R2t, where R1 and R2 are the two possible values for R here. And there are other solutions that are just as viable. We could get something that looks like this. C1 cosine omega t plus C2 cosine, not cosine, sorry, sine omega t. And in some situations we can even get something that looks like this. C1 plus C2t e to the rt. All three of these are completely different behaviors, and this is something you would learn in a differential equations class. These are exact solutions to this differential equation. If you went and substituted these in here, you would get the you'd find that it does in fact hold true. However, that's not necessarily the case. I just realized I made a small mistake. These are all the homogeneous solutions. That's assuming that this term right here is equal to 0. When it's not equal to 0, you have to add a second term, which is the particular solution. And this depends on your function, your external force, xp of t. Obviously, this is something you learned in a differential equations class. However, keep in mind that not all systems are as ideal as this system, right? So we've assumed quite a bit actually when we derived this equation. Most notably here, and most notably there actually, which is that the spring force is perfectly linear for all displacements, and the viscous force is perfectly linear with all velocities. If we were to get a little bit into the specifics, hopefully not too much, we would realize that the spring constant is actually not very linear, as you have large amounts of deformation. For example, we have a linear region, but then maybe we have, a curve breaking off. I might have drawn this wrong. I don't have it open with me right now, but we have a linear region in here where our spring behaves elastically, right? This is Hooke's law. A material would obey that. However, with large deformations, such as here, you get deviations because of plastic deformation, or maybe the material breaks. And a very similar argument can be made for velocity, right? As if for those of you who have looked into aerospace and aerodynamics and drag, you'll know that the force of drag is proportional not only to the velocity, but also to the velocity squared. So if your velocity is too high, this term starts to kick in, and then we have an equation that is very difficult, if not impossible, to solve by hand. And so the exact solutions that we have down here, these are valid under the assumptions that these two forces behave perfectly linearly, and that we don't cross into this nonlinear region off to the sides. That being said, they are still very good approximations, and it definitely helps to know where these equations come from and what they mean. However, a numerical solution is very much preferred when we have to account for nonlinearities, such as the force of drag and whatnot. So from here we have to think about how do we simplify a differential equation into a form that can be solved very easily by a computer. And that's where we have this topic called reduction of order. Reduction of order, if I'm not misspelling it. And the idea is to take a second order differential equation, so take one second order differential equation and turn it into two first order differential equations. And this might seem a little weird to those who haven't taken a differential equations class, but this will make, hopefully, with this example, it will make perfect sense. So let's start with our system from before, which is mx double dot plus bx dot plus kx equals f of t. And let's use a bit of a substitution. Let's define a new variable called x1. Let me give myself a little bit of space. x1. And we're going to make this equal to x, and we're going to use x2 and set that equal to x dot. A very weird transformation, considering, why can't we just write x2 as x double dot 1? And we'll see where this comes in. Well, let's write down the equation. Let's expand on this a little bit. Let's take the derivative of x1 and x2, and let's try to write it so that we only have x1 and x2. Note, this is a first order differential equation if we only have first derivatives here and no derivatives here. So, the derivative of x1, well, the derivative of x1 is the derivative of x, which is x2. Okay, that's pretty straightforward. And the derivative of x2 is the derivative of x dot, which is x double dot. Well, we can extract that from here. So, let's do that. Let's move everything off to one side. So we have mx double dot is equal to f of t minus bx dot minus kx. And then we move the m term out. So 1 over m times f of t minus bx dot minus kx. Okay, this is pretty straightforward. Let's put that in here using this substitution as mentioned before. So we have 1 over m, pretty straightforward, f of t minus b x dot. Well, x dot is equal to x2, so let's write that x2, and minus kx. But kx is just x1. And so, if you look at this carefully, you'll realize that this is in a very peculiar form, where we have a first order derivative here. Let's call this general vector right here x, and we'll call this some function of x, right? Because we can substitute x1 and x2 in here, and this is the expression we get. So the form of this is x dot is equal to some function of x, and we have this little t, so we can also add that t. And it turns out that this form right here is very, very easy for computers to numerically approximate. We'll get into the specifics further down the line, but what this is saying is the slope of the function depends on its position and the time that we are at. And this is very helpful because, if we know the slope at a certain point, let's say we know that the slope at this point is this value. Well, then what we can do is we can actually compute the slope at some point x and t. We can compute it at some t, this is x, some t and x. And what we can do is we can take a small step forward, right? So we can rewrite this as dx dt equals f of xt. And so applying a little bit of calculus, we can actually derive Euler's method. Once again, we'll do this in the next video, but in a sense we can take a small step forward in time. Actually, I'll just do it right now. So we can get dx is equal to f of x comma t dt. Take the integral of both sides. Obviously there's a bit of caveats here, but we can get x is equal to x naught plus dt. Sorry, whoops, wait, I made a bit of a mistake. So this is so we would have to take the integral, but I'm making a few errors here, but I will clarify this in the next video. But essentially the form that we pull out of here is that x of the next step is equal to the previous step plus the derivative and the time step that we are taking. And this right here is the basis of Euler's method, and what it says is that, let's say we start down here, we can figure out the slope and take a small step forward in time. This would be our t plus dt, and it will give us a value which is going to be our x. Let's say this is xn, this is going to be xn plus 1, the next step forward. And then here we can calculate another value, take another time step forward, and slowly we'd be able to draw, oops, that's a bad curve. We would slowly be able to draw the curve that approximates our solution. And this is the idea behind numerical analysis and solving equations by numerical method. Obviously, I'm not a master of this, as you could see from here, but the overarching idea should be pretty familiar now. Let's see. And this is the basis, yeah. So next video, I will go through and actually, well, first up I will clarify this little mistake I made here and actually derive Euler's method for solving differential equations. And then we will explore the next step, and then we will explore furthermore for the further steps and further formulas that we can use to approximate solutions. And then, yeah, we will actually implement some of these in MATLAB. Alright, that is all for this video. We'll see you in the next.